All right, in this lecture, I want to talk about something called electrostatic pressure. And basically what electrostatic pressure is, it's a way to understand, or to calculate rather, how an electric field can exert pressure or a force per unit area on a conductor. Let's say I have a conductor in an external electromagnetic field. Okay, this is my conductor here. In this field, it is going to accumulate a non-uniform surface charge that is going to balance out this external electric field so that I have an electric field equal to 0 inside my conductor. Okay, in order to do that, we're going to get an accumulation of negative surface charge on this side and positive surface charge on the left-hand side here. Okay, if I were to draw a little Gaussian surface here, let's see, a little better. If I were to draw a little Gaussian surface to try to understand how the electric field just outside my conductor, so E right here. Okay, so basically I'm going to take this width and shrink it down to 0. I want to understand how the electric field just outside the conductor is related to the surface charge density. Again, I could do this game here where I get my electric field dotted with dA is going to be equal to the enclosed charge within that little Gaussian surface over epsilon naught. This left-hand side is going to be my perpendicular component of the electric field times A. And then it's going to be added to 0 times A for the inside, and then 0 for the walls. So that's going to give me Q enclosed divided by epsilon naught, right? And then when I divide both sides by A, I end up getting the charge density divided by epsilon naught, or I can rewrite this as the electric field is going to be equal to my charge density divided by epsilon naught in the n hat direction just outside my conductor. Okay, so I know that there is a little bit of electric field here just outside my conducting surface, and that a little bit of electric field is actually going to exert a force on the conductor itself. So the question is, what force does E external exert on the conductor itself? Well, if I want to describe the force, remember force is equal to Q times the electric field. I can divide both sides of this equation by the area. I'm going to get on the left-hand side here little f, which the book describes as the force per area, which of course is the same thing as pressure, being equal to Q over A times E, okay, which is the same thing as sigma times E. Okay, so just to write that together, I get that the force is equal to sigma times the electric field. So what that tells me is if I had some kind of conductor and I took a little bit of area, then I would have a force here, a force per unit area that was in the same direction as an electric field, okay? Is related to that charge density, which is on my area here, okay, times some electric. If I want to determine the force on our patch with our area A, we need to know the charge density of that patch and the electric field at the patch, okay? As the book argues, the charge density is simple enough, but the electric field right here, right at the patch, is kind of complicated, right? because on this side, I know that the electric field is equal to 0, but just above the patch on the other side, right, I know that the electric field is equal to the charge density divided by epsilon naught in that normal direction. Okay. The book does a nice job explaining a technique for figuring out the electric force or the electric field that causes the force on the patch. And that ends up being the average of the electric field above and below the patch. That's kind of handy. And when you take the average of that electric field above, it's going to be equal to sigma over epsilon naught in the n hat direction. Below, it's of course equal to 0. Might as well say that's in the n hat direction. Why not? Divided by 2, so you end up getting that the electric force felt by that patch of charge is actually half of our electric field just outside the patch. Okay, so this is the electric force electric field that's causing a force on this little bit of a patch. It's not the full electric field just outside the patch because there's this big discontinuity in the electric field, so it's actually the average of the electric field on this side and on that side of our patch. Okay, so if I plug that in, then I get the force per unit area on the patch is going to be equal to sigma times sigma over 2, needs to be a naught here, epsilon naught, and that is in the n hat direction. Okay, so I get a force that's equal to sigma squared over 2 epsilon naught n hat. So again, whether this patch is positively or negatively charged, it's going to go away because we're going to square our surface charge density. So if it's negative, it's going to go away. If it's positive, it's going to stay positive. It's going to exert a force on our little patch, okay, that is normal to the surface, okay? So let's think about what this means if I put a positive charge conductor, instead of putting in a uniform field, I'm going to put it next to a positive charge like that. Well, in this case, I'm going to get a larger charge accumulation here than I'm going to get over on this side of my conductor. And the reason for that is, right, we need to cancel out this electric field from this positive charge inside the conductor, but that electric field is, of course, dropping off like 1 over r squared. Okay, so when I think about the electric pressure, our electrostatic pressure, which is going to be equal to 1/2 sigma squared over epsilon naught in the n hat direction, because I've got a larger charge density here than I do over here, this force vector is going to be larger on this side than it would be on this side, okay? And this conductor would be what the book calls drawn into the field, or it would have a net force to the right. Okay, so the net force, the force on this part of the conductor, would be greater than the force on that side. And that kind of acts like a pressure. If I wanted to rewrite this pressure in terms of the electric field instead of in terms of the charge density, I would write it as the pressure is equal to epsilon naught over 2 E squared. And that, by the way, just comes from the fact that sigma is equal to E times epsilon naught. Okay. This basically tells you, if I look at this equation here for the pressure, the pressure is going to be greater on this side than it would be on that side because E1 is greater than E2. Or the strength of the electric field is greater on the right-hand side of the conductor than it is on the left-hand side of the conductor. Okay, so I hope that helps you understand how electrostatic pressure can actually draw a conductor into the field or into the stronger field due to the difference in force per unit area experienced by different parts of the conductor.